Hello, my dear students. Hope you are in good health and spirits. And I welcome all of you again on this online learning platform at 4Pi Academy. And we are discussing the atomic and molecular spectroscopy. In this third lecture, we will discuss a very important topic that is the Rydberg constant and how these Rydberg constant value it varies with the change in the nuclear mass, and then we will drive the relation of this Rydberg constant for different energy spectral series. We will drive for Lyman series and how these Rydberg constant it is dependent upon the value of this wavelength. And after that we will discuss about the positronium ion and about the helium ion, and then we will compare the value of this positronium ion with the hydrogen atom, and then we will discuss the numerical problems. We will discuss those numericals which are coming from GATE, CSIR, JEST and TIFR competition examination in previous years. So let us start our lecture. So our first topic of today's lecture is the variation in Rydberg constant due to finite nuclear mass. So first of all, I would like to explain about what is Rydberg constant. So the Rydberg constant, so it represents the limiting value of highest wave number, or we all know that wave number it is inversely proportional to wavelength, or you can say it is the shortest wavelength. So that we have already discussed in the series limit of any proton or any photon that can be emitted from hydrogen atom or hydrogen like atoms, and we generally derive the wave number that is the inverse of wavelength and whose value is R infinity 1 over nf square minus 1 over ni square, and it is also dependent upon the atomic number of the atom. And the value of this Rydberg constant that is for the shortest wavelength, or you can say for the series limit, we generally represent it m e raised to power 4 e epsilon naught square hc. And for this shortest wavelength, the value of this Rydberg constant that is for a infinite nuclei that is of the order of 10 to the power 7 meter inverse. And you can check from this series, and this is the series limit, that is the value of the series limit for the Lyman series, that is we have already derived, it is around 911. And similarly the value of this wavelength it increases with increase in these energy levels. And how we can derive the value of this Rydberg constant? So the value of Rydberg constant for a infinite nucleus mass, so that is of the order of 10 to the power plus 7 meter inverse, and this value for a finite nucleus mass it decreases. So the value of Rydberg constant it decreases with the decrease in nuclear mass, and this we will derive now. So derivation of Rydberg constant Now if we suppose that, so this is our infinite energy level series and we represent it as the initial level, and this is for our final state, that is suppose it is 1, and we generally call it as the Lyman series limit. So we will first of all derive the value of Rydberg constant for Lyman series limit, and then we will compare its value with Balmer series, Paschen series, Poufand series and bracket series. And so the value of this initial energy state, that is infinite, the final energy state, it is equal to 1, that is our Lyman alpha series. So the wavelength, it is 1 over lambda, that is R infinity 1 over nf square over ni square, and the value of Z, that is for hydrogen atom, it is equal to 1. So Z is equal to 1. So here Z square, it comes out to be 1. So this becomes R infinity final is 1 over 1 square minus 1 over infinity square. 1 over infinity is 0. So 1 over lambda, that is equal to R infinity. So we all know the value of this lambda, that is for the Lyman series, it is of the order of 911, and from that we can calculate the value of Rydberg constant, that is 1 over 911 into 10 raised to power 10 per meter. So when we calculate it, it is coming of the order of 1.097 into 10 raised to power 7 meter inverse. So this is the maximum value of Rydberg constant. So when any spectral line series which is falling from infinite to first energy state, so that is the maximum value of series. And from here I would like to mention that the Rydberg constant, it is inversely proportional to wavelength. So the value of Rydberg constant, it decreases with increase in wavelength. So the value of R, it decreases with increase in wavelength. So similarly we can also calculate, so the value of 1 over lambda, that is for Lyman series, this we generally represent as R infinity over nf square, and for Balmer series we all know that the value of this nf, that is equal to 2, and ni, that is equal to infinity. And similarly, by putting the value in the previous equation, you can calculate the value of Rydberg constant for Balmer series, and it is coming of the order of 4 over lambda. And similarly for Paschen series, where nf is 3, and from this equation you can calculate the value of Rydberg constant, it is coming of the order of 9 over lambda. And similarly for bracket series, where nf, that is equal to fourth energy spectral series, and the Rydberg constant value, it is 16 over lambda. And similarly for Poufand series, so therefore as there is a change in wavelength for each energy spectral series, so the value of this Rydberg constant, it is changing with respect to wavelength. So therefore for Poufand series we know that the value of nf, that is equal to 5, and it is coming of the order of 25 over lambda. Now we will do some examples of the change in Rydberg constant for helium and for hydrogen. So first of all, I would like to explain how this Rydberg constant it changes for a finite nuclear mass. So until now we are talking about the variation of Rydberg constant for a infinite nuclear mass. Now we will derive the variation in Rydberg constant due to finite nuclear mass. So for infinite nuclear mass, the value of Rydberg constant which we have derived, that is m e raised to power 4 8 epsilon naught square hc cube into c. So let us say this is equation number 1, and for finite nuclear mass, now suppose we are having a nuclear mass whose value is m. So the Rydberg constant for that particular finite nuclear mass, so it is equal to mu e raised to power 4, where mu is the reduced mass for that particular nuclei, over 8 epsilon naught square h cube into c. So mu, the reduced mass which we can calculate, that is m into capital M over capital M plus small m. Here m is the mass of the electron which are present around that particular atom, and this is our nuclear mass. So this is our electron mass. So let us say this is equation number 2. Now we divide these two equations. So from here we get a equation R infinity, that is for infinite nuclear mass, over Rydberg constant for a finite nucleus mass, that is Rm. So it comes out to be 8 epsilon naught square h cube over c into mu epsilon naught 4 over 8 epsilon naught square h cube over c. So these get cancelled. So what we are left with is m over mu. So the value of this Rydberg constant, so putting the value of this reduced mass, so that is m into capital M over m plus m. So it comes out to be m into m plus m over m into capital M. So that is equal to m over m plus 1. So this Rydberg constant for two different nuclei, so that is of the order of m over capital M plus 1. Or you can say, so the Rydberg constant of a finite nuclei, that is R infinity over 1 plus m over capital M. So from this equation you can clearly see that the value of Rydberg constant for a finite nucleus mass, whose value is less as compared to the value of this Rydberg constant for infinite nucleus mass. So Rm is less than R infinity in all the cases. So the value of Rm, it is different for different atom. So for a infinite nucleus mass which we have derived, so whose value is maximum, that is of the order of 1.097 into 10 raised to power 7 meter inverse, or you can write it in centimeter, 109740 centimeter inverse. And this is for infinite nuclear mass. Now let us solve the value of this Rydberg constant for hydrogen atom. So for hydrogen atom, if we have to calculate, now for hydrogen atom, the ratio of m over m, that is generally 1 over 1836 times, because we know that the mass of proton, it is quite heavier, that is of the order of 1836 times the mass of electron. So here this is mass of electron, this is mass of proton. So the value of Rm, if we put it in the equation, that is 1 plus small m over capital M, and when we derive it here, Rm, that is equal to Rh, that is for hydrogen atom. So the value of Rydberg constant for hydrogen atom, it is coming out to be 109677 centimeter inverse. And when you relate these two values, so this is for hydrogen atom and this is for infinite nucleus mass, and you can check that, so there is a change in Rydberg constant. So here the value is 109740 and here the value is 109677. So the value of Rydberg constant for hydrogen atom, it is less as compared to the Rydberg constant for infinite nuclear mass. Now if I draw a graph, so if I take here this side the mass number, and on this side if I take the value of Rydberg constant, and this is the maximum value of Rydberg constant, so that is for infinite nucleus mass 10967740 centimeter inverse, and for hydrogen, so here it is having this value. So for deuterium 1H2, it is having this value, and the trend of this graph, it is something like this. So here it is helium, here it is lithium, here it is oxygen. So you can check that as the atomic mass number is increasing, the value of this Rydberg constant, it is increasing and it is approaching more and more towards the value of R infinity. So for a lighter atomic nuclei, so 1H1, that is for hydrogen atom, the Rydberg constant has a lowest value, and for deuterium for 1H2 it is having larger value, for helium it is slightly greater, for oxygen it is more greater. So from this trend of graph we can say, if we increase mass number, the Rydberg constant approaches more and more closely to R infinity. Now let us calculate the Rydberg constant for helium atom, and from here you can also get a more clear result. So for helium atom it is R infinity over 1 plus m over mass of helium. Now we know that mass of helium, so that is 4 times the mass of hydrogen atom. So this equation becomes R infinity over 1 plus m over 4 times the mass of hydrogen atom. But we know that m over mh, that is of the order of 1836. So for helium this equation becomes R infinity over 1 plus 1 over 4 into 1836, and when you calculate it, so it comes out to be 109740 into 4 into 1836 over 4 into 1836 plus 1, that is of the order of 109740 into 0.9998. So that is equal to 109725. So again this is the maximum value, that is for infinite. So this is coming out to be for the helium atom. Again this value is less as compared to the Rydberg constant for a infinite nuclear mass. Now, but the value of this Rydberg constant for helium, it is greater as compared to the Rydberg constant for hydrogen atom. So this you can check from this graph. So similarly, sometimes there is a question that is for the deuterium atom. So which you also known as the heavy hydrogen, which we generally represent as 1H2. So the Rydberg constant for deuterium, it is, again you can calculate 1 plus m over md. So the mass of deuterium, it is 2 times the mass of hydrogen, because it has 1 neutron and 1 proton. So the value of Rd, it comes out to be R infinity 1 plus m over 2 times mass of hydrogen. So putting these value m over mh, so this we know that it is 1836. So this comes out to be 109740, 1 plus 1 over 2 into 1836. So the Rydberg constant for deuterium atom, it is coming out to be 109707 inverse. So again the value of this Rydberg constant, it is less as compared to Rydberg constant for a infinite nuclear mass. Now, before moving to the next topic, I would like to explain some important point about the positronium atom. So, positronium atom. So, positronium atom is a system consisting of an electron and its antiparticle, so that is the positron. Now the antiparticle of electron, that is positron, so we generally represent electron as E negative, while the positron we represent as E positive. So what is the major difference between these two particles? Now both these particles, so they have having same mass but different charge. So electron which is having a negative charge, while the positron which is having a positive charge. Apart from that, so both these particles, so they belong to fermions, so which is having half integral spin. Now what is this positronium system? So let us say this is our nucleus. So this is the electron which is present in the hydrogen atom. So hydrogen atom, which we generally represent as 1H1, so which is having 1 electron, 1 proton and 0 neutron. Because we know that, so here it is represented as the atomic number, so the Z, that is representing the value of number of protons present in a nuclei, while the N represent the number of neutrons, so which is A minus Z. So for hydrogen, so there is no neutron. So similarly for helium, so there are 2 electrons, so which are present in the first atomic orbital. So it has 2 electron, 2 proton and 2 neutrons. So from this you can also calculate. And similarly for positronium atom, so this is 1 electron and this is the positive particle. So we generally represent it as 1 electron and 1 positron. So because they both exist in pairs. So positronium is a system consisting of an electron and its antiparticle, that is positron. Now how we can identify the velocity of these positronium atom? We can identify the Rydberg constant, what will be the reduced mass this positronium. So let mass of electron, that we generally represent as me, which is m, and we know that both the particle and antiparticle, so they are having same mass. So mass of positronium, that is also equal to mass of electron. So mass of electron, that is equal to mass of positron. So positron is a two body problem. Is a two body problem Now if we convert it into a one body problem, so by calculating its reduced mass, so in order to solve our numerical problem, so the reduced mass, that is the sum of these two masses which are present in this positronium atom, mass of electron 1 over mass of positron. So both the masses, they are equal, so 1 over mu, that is 1 over m plus 1 over m. So the value of this 1 over mu, that is 2 over m. So the mass, reduced mass of this positronium atom, so that is m by 2. So this is a very important result. So the mass of positronium atom, so we can write it as PS, so that is the half mass of hydrogen atom. Now we can compare this positronium atom with hydrogen atom. So we can compare its energy, we can compare its velocity. So the relation, so I will write in shortcut. So the energy of hydrogen atom, so which we have already derived. So energy of hydrogen atom, so that is minus R infinity Hc over n square. So you can check from this formula where the value of this Rydberg constant, so that is 8 epsilon naught square h cube c. So EH, that is minus m raised to power me raised to power 4 Hc over 8 epsilon naught square h cube c into n square. So this EH, that is minus 13.6 over n square electron volt, so that is for hydrogen atom. And similarly for positronium atom, so that is for positronium atom, the value of this energy, that is minus mu e raised to power 4 8 epsilon naught square h square n square, and the value of this EP, putting this value, it comes out to be EH by 2. So therefore the energy for this positronium atom, that is half that of hydrogen atom. And for each energy spectral limit, you can calculate the energy of this positronium atom, and that is different for different spectral energy limit. So this relation is quite important for numerical point of view. And similarly you can derive the relation of velocities. So velocity of electron in hydrogen atom, so that we have already derived, that is Z square over 2 NH epsilon naught. So from this formula we can say that the velocity of electron, it is independent of mass. And it depends only on number of orbit n in which that electron present is. So similarly for positronium, so the velocity will be same. So therefore velocity of electron in hydrogen atom and velocity of positronium in a velocity of electron in positronium atom, it is the same for the same orbital electron because it does not depend upon the mass. And similarly you can calculate the radius for this both hydrogen and positronium atom. So radius for hydrogen which we have derived, that is n square h square epsilon naught over m pi z square. Again it is dependent upon the electron mass. So radius for positronium, that is n square h square epsilon naught over mu pi z square, where mu we know that is me by 2. So the value of this positronium radius, that is 2 times the hydrogen radius. So what does it means? Radius of positronium atom is 2 times of the radius of hydrogen atom. So similarly you can calculate or compare the value of the Rydberg constants. So Rydberg constant here I will derive in this portion. So the Rydberg constant for hydrogen, that is me raised to power 4 over 8 epsilon naught square h cube c, and as you can see it is dependent upon this mass. So the Rydberg constant for positronium atom, so this is the result for Rydberg constant. So Rydberg constant for positronium, it is mu e raised to power 4 8 epsilon naught square h cube c. Again the value of this mu, that is half of the mass of hydrogen atom. So the Rydberg constant for positronium atom, so it is half of Rydberg constant for hydrogen atom. So these are the results of Rydberg constant. So based on these values we will solve some of the numerical problems. So our first numerical is the wavelength of a spectral line in positronium atom which corresponding to Lyman alpha line of hydrogen atom is. So this is the question of CSIR 2010 examination. So for alpha line, so that is the first line of Lyman series. So n, that is final, that is 1, and initial, that is 2. So Rydberg equation, it becomes 1 over lambda 1 over h 1 over nf square over 1 over ni square. So 1 over lambda h, that is for the hydrogen atom, it comes out to be 3h RH over 4, because NF, that is 1, so this 2 square it becomes 4, so that is RH 1 minus 1 over 4, so that is 3 RH over 4. So this is, let us say, equation number 1. Now for the positronium atom, 1 over lambda ps, that is Rydberg constant for positronium atom, 1 over 1 square over 1 over 2 square. So the Rydberg constant, we know that for positronium atom it is the half of the hydrogen atom. So from that lambda ps, so that comes out to be 3 Rydberg constant for positronium over 4. So putting the value of this rps in this equation, so this becomes 3 by 4 into 1 over 2 times the Rydberg constant for hydrogen atom. So this we can write 3 RH over 4. So this 3 RH over 4, so that is our equation number 1. So that is equal to 1 by 2 into 1 over wavelength for hydrogen atom. So therefore the wavelength for positronium ion, it is 2 times the wavelength for hydrogen atom. Now the wavelength for positronium ion, so that is for the alpha line series, so that we all know, we have derived in our previous results, so that is of the order of 1215 angstrom, or you can also calculate from this equation number 1 by putting the values, and it comes out to be 1215 angstrom, that is for the hydrogen atom for alpha line. And therefore for positronium it is 2 times the wavelength of the hydrogen atom, and it comes out to be 3 angstrom, and this is close to the value of this B. So the correct option is option B. So next question is, an accelerated beam of electron bombarded on a sample having hydrogen atom, and the first line of Paschen series is emitted. The electron must have been accelerated through a minimum potential difference of. Now what the question saying is, so there is a electron which is being bombarded by hydrogen atom, and hydrogen atom, they are at rest when we bombard these electrons to this hydrogen atom, and so this is 1. So these electrons, so they get accelerated and reach to the value of n, that is equal to 4, and the electron must have been accelerated through a minimum potential difference. Now we all know that the Paschen series, so for Paschen series the value of n, that is equal to 4. So therefore the energy difference E4 minus E1, that we can calculate, that is the EV naught, where EV naught is the electrostatic potential which is being generated between these two energy levels, and the value of E4, that is we can calculate from the Bohr energy formula, that is 4 square minus, for first energy line it is equal to 1 square electron volt, that is equal to EV naught. So this comes out to be minus 13.6 over 16 plus 13.6 electron volt, that is equal to EV naught. So this E get cancelled, and this comes out to be minus 0.85 plus 13.6, so that is equal to V naught, so which comes out to be 12.8 volt. So this is the value that the electron, it must get accelerated at a potential, that is the minimum potential is of the order of 12.8 volt. So next numerical is consider the spectral lines resulting from the transition from N2 to N1 state in the atom and ions. Calculate the shortest wavelength which will be produced in which case. Now we know that when there is a transition from 2 to first state, so we know the relation, that is 1 over lambda, that is R infinity 1 over NF square 1 over Ni square into Z square. So therefore if we compare all these four values, so for hydrogen atom, so there is one proton and one electron, and for deuteron atom there is 2 times one the mass of one proton and one neutron, and there is one electron. And for single ionized helium, so that is for helium plus atom, so there are 4 MP and there are electrons. And similarly for double ionized helium atom, so there are 6 यानी कि 3 neutrons and 3 protons, so they are present. Now if you can relate that the value of this 1 over lambda, so it is directly proportional to Z square. So 1 over lambda is larger when Z is larger. So what does it means? So the wavelength, it is inversely proportional to the atomic number. So what does it means? The shortest wavelength is produced with those atoms which is having high atomic number. So shortest wavelength is produced by helium plus ion because it is having high atomic number. So therefore the correct option is doubly ionized lithium atom. So moving towards our last numerical, so this we have already derived, and this comes in the Tata Institute of Fundamental Research exam in 2013. Now what they have said is velocity of an electron in the ground state of hydrogen atom, it is Vh, and if Vp the velocity of an electron in the positronium atom, then derive the relation. Now we know that the velocity formula, that is Z square over 2NH epsilon naught, and it is independent of mass. It does not depend on mass. So therefore the value of the velocity of electron in the positronium ion, it is same for the value of electron which is present in the hydrogen atom for a particular orbital. So therefore our correct option is option A. So this is all about our today's lecture, and hope you have enjoyed our lecture. And if you have any query, so you can provide your review for this course, so by giving your valuable review in our website, and you can ask any query by writing your question in the comment box, or you can write any doubt, then we can discuss or provide you the best solution. So till then, goodbye, see you in the next lecture. Keep watching 4Pi Academy.